Okay, in this video, let's start with number 4 because it probably flows best from what we just did in number 1 and 2. So again, you can see that we have a problem that the potential energy function is given by this. I just wrote it right here. Where B and C are constants, which of the following is an expression for the force? And again, the force is going to be equal to the negative derivative of this. So that's going to be, I'll bring the negative 3/2 out. So 3/2 BR. Reduce this by 1, so it's kind of like I'm subtracting a 2 minus a 2. And so I'm going to get a negative 5/2. And then my negative and negative becomes a positive. So you can see that's going to be 3/2 BR to the negative 5/2 power. So that's pretty clear right there. All right, let's jump down to number 5. Number 5 is not hard. Honestly, it's an old AP question. And the reason I pulled it out is I could see us getting a question that somebody gives us a potential energy graph and asks you to draw the force graph. This problem, however, is kind of a bad one. It's a free response problem from a while ago where we're not quite sure where the segments are. So I'm going to explain it to you, but just know that they write cleaner problems today, that this ambiguity would not be there. All right, so if I look at this, this is a potential energy curve, and I know that the derivative of the potential energy curve is going to give me the force, but I got to throw the negative in. So when I say derivative, I'm talking slope of the line. So I can see here that from 8 down to, I'm just going to stop right there, down to like 1.5, it looks like the line is pretty straight. So I'm just going to find the slope of this line. So down from 8 to 2 is my rise. So that is going to be, what, a 6 over a run of 1.5. And so the slope of this line is a -4. But because I got this little negative sign hanging there, I have to take the negative of that. So the negative of the -4 becomes a +4. So the slope, or the force, from 1 to 1.5 is a +4. So I'm just going to graph that, +4 up to 1.5. And I'll just leave that there. And then I notice that from 2 until, I don't know, I'll call it like close to 5, right here, 2 to 5. This looks kind of straight. And so the slope of this line is going to be, this is a 1, 1 up to 4 would be 3. And this is over 1, 2, 3, 3 over 3. So it looks like the slope is a +1, but remember the negative sign there, so it's really a -1 from 2 to 5. So from 2 to 5, I'm going to put in a -1. And this is the part that's sloppy in this problem. So I just know that somehow these things kind of have to hook together, and I can kind of hook them together like that. They don't have it that way anymore. You're going to be used kind of more of your calculus notation in terms of how to hook the lines together. But that's all they had to do back in the day for this little curvy thing here. And then I could just kind of round these off and say that maybe from, I don't know, I'll say 5.5 to 7. So the last 1.5 here, I have 1, 2, 3. So I have a rise of 3 and a run of 1.5. So that looks like the slope of this is -2. But because of this little negative sign, it's going to become a +2. So from 5.5 to 7, it's going to be a +2. So 5.5 to 7 is a +2, and then I can just kind of hook those together like that. But again, if you have potential energy in displacement, you can sketch the force versus displacement graph just by knowing that the force is equal to the negative slope of the potential energy curve. All right, let's then go up to number 3. I like number 3 because it's, I'll say, a different approach. So on number 3, they give us a potential energy curve. But the question is, if the particle is released from rest, so it has an initial velocity of 0 at position R0, so I'll say at R0, its speed at position 2R0, I want to know what the velocity is right here. When I know that the velocity at R0 was 0. So they're not asking me about force, so I'm not going to worry about the slope area under the curve stuff. They're talking to me about potential energy that I can read off a graph, and they're asking me about velocity. That's my clue that I'm going to treat this like a conservation of energy problem. So I'm going to say at the start of the story is going to be, or spot 1 is going to be R0. So at R0, I want to know about the potential and I want to know about the kinetic. So I want to find like the ET at spot R0. And that has to equal the ET at spot 2R0. So at spot 2R0, I want to know about the potential and I want to know the kinetic. And I'm actually looking for the velocity that's going to be hidden in this kinetic energy here. So this is nothing more than reading the graph and writing down what it says. So we do know the position at R0, or the potential energy at R0. So at R0, the potential energy is, let's just read it off the graph, 3U0. I'm going to write that down, 3U0. We know that the kinetic energy at R0 is 0 because it starts at rest. So plus 0, I'll just cross that out, equals. And then over here at 2R0, right here, we can read the potential energy right off the graph. It's U0. So then I'm going to say plus KE. I'm going to be solving for this KE. So to solve for this KE equals, I'm going to subtract a U0 from both sides. So that will make this a 2U0. So I'm going to bring this over here, and 2U0 is going to equal, I'm going to expand this kinetic energy to 1/2 mv squared. And I'm solving for speed, so I'm actually solving for v. So v squared is going to equal, I'll multiply both sides by 2, so that's going to become a 4. And then I'll have to divide both sides by m, and then if I square root it, I'll get v. So again, nothing more than interpreting the graph, reading the potential energy off the graph, and using conservation of energy. I think that's a very creative problem, and something I could see that could be a really kind of cool question. So make sure that you study this one, and because it's different than the other ones. And 1, 2, 4, and 5 all used this relationship down here. So this relationship is kind of like the summary of the whole force and potential energy information that you need to know.